Yeah, much better. My name is Shani Samuel. I am a field application specialist for Beckman, and today I want to talk to you about the ways in which we have designed and tested a high throughput platform for bacterial cells that we have tweaked for Pichia and methylotrophic yeast in general. The setup that you see on the left-hand side is a commonly used fermentation platform that you would often see. Generally electro-based, generally higher volume than what we can provide, or that what we'd like to provide, but it's lower throughput. And if you have quite a few strains that you'd like to test on the upstream process of your process, this can be quite time-consuming. So what we've done is miniaturize this process into a 1 milliliter volume. And we've changed it from an optode, or not an optode, we've changed it from an electrode-based measurement platform to an optode-based one with the BioLector XT. So the BioLector itself was designed with bacteria in mind specifically, and we have a very specialized plate that we can use to better recapitulate what's going to happen on the larger scales. So each well, there's 48 wells within a plate. Again, it's a plate-based reaction. And each well is embedded with what we call optodes. It's a polymer cocktail that responds to changes in pH and dissolved oxygen, but it also allows you to measure biomass and fluorescence. And this gives you all of the bioprocess parameters that you need to know on the larger scale so that you can make a more informed decision once you start scaling up. The plates themselves are quite a specialized part of our technology. The optodes will respond to differences within the culture. So for the DO optodes, anything that is, any oxygen that's dissolved within your culture, the optode will change colors based on how much oxygen is available within the broth. Similar to the DO optode, the pH optode changes, it will change colors based on what the pH range is that's present within the broth. So because you're getting online measurements basically of what's happening within that culture at that time, it really creates a more high throughput platform that you can respond to. One of the special things I think about the plate that you can use with the BioLector is changing the geometry. Can you guys see that? That you can change the geometry. So in many of the experiments that I'll show in just a few slides, we use the patented flower plate. And it's got these baffles along the outsides. This helps to mix the solution and also aerate oxygen within the culture. And as we kind of know, oxygen that can get dissolved within the culture can then be available to use by your culture. The optodes themselves, we have had a kind of a long-standing, I guess, technology that would have otherwise used the pH range of about 6 to 8. But for Pichia and methylotrophic yeast in general, this became a problem that we had to address. So what we've done over the last couple of years is introduced a new optode that can be used for the lower pH ranges. So previously, it would have been in the pH range of about 6 to 8, and then now we can measure lower pH ranges in the more optimal for Pichia, and that's about 4 to 6. You can go. Yeah. Oh, there's also a scattered light signal based on the fiber optic. There's a fiber optic that moves along the bottom part of the incubation chamber that takes measurements in very specific spots on the plate for every well. So you can technically get individual reactions, 48 individual reactions that happen over the course of the plate and get online measurements of all of those without you having to do any manual sampling yourself. And this slide here is kind of proof of principle of what we can do using Pichia. So, yeah, using Pichia. So it's a scattered light signal that we use for biomass, but that correlates on a one-to-one basis with OD600 and cell dry weight. So any of the growth curves that you would otherwise see in your spectrophotometer, you can do that plus more with the BioLector. The scattered light signal is quite special. One of the limitations of plate readers and spectrophotometers in general is that once you have a high data, or not data density, but once you have a high culture density, taking a beam of light and making that go right through the high density culture, you'll generally saturate your detector, and not enough light will make it to the detector, which means that you'll end up having to do dilutions in order to just know what your actual culture density is. But because we use a scattered light signal with the biolector, you don't have to do any dilutions, and any of the growth curves that you end up seeing with the biolector hold true, thank you, hold true for, they hold true when you do that same experiment with the biolector. So without any dilutions, you get the same growth curves that you would have otherwise had in a plate reader doing dilutions with the biolector. The plates themselves are quite special. We have very well-defined mass transfer conditions. So this is what we've gotten for oxygen transfer. And as you know, only the oxygen that's really going to be dissolved within the culture is available to use. So for high oxygen consuming strains, it really won't matter. Well, it will matter greatly how much oxygen you can dissolve within the culture. So there is an inverse relationship between how much you can shake the plate itself and how much oxygen you can get dissolved within the culture. So at a particular shaking speed, we can tell you exactly how much is possible, how much oxygen is actually possible to get within your broth. So using those defined mass transfer conditions, we then tested it. So this is some data that we collected with E. coli, where we adjusted the shaking speed, the fill volume of how much volume is within the well at a particular time, and we also changed the geometry of the well itself. So all the data that you saw with the defined mass transfer conditions were with the flower plate, but we also have a round well geometry that you can also use. So when we're looking at a lower shaking speed with a round well geometry, you then get to really see the effect of oxygen limitation on the growth of your strains. So as we fill the well more with more volume, you then get to see a slowdown of growth. As you increase up the shaking speed, still with the same geometry, that effect is reduced. But if you use our flower plate that has high mass transfer or high oxygen transfer conditions, it's reduced even more, even at the lower shaking speeds, and it's virtually eliminated. Excuse me, it's virtually eliminated when you use the flower plate with a higher shaking speed. So we now get to tune our experiment to play better with the strain, with the place that the strain is at that current time, instead of just working with the limitations that we were given. So we just really get to see a really high impact example of how oxygen limitation can really slow down the effect of your growth, and what things we can do to eliminate that. The experiments that I will show you on the next couple of slides use our microfluidic plates. So the same pH and DO cocktail with the optodes can be combined with microfluidics. And the microfluidics will then allow you to feed actively and also change pH. Because we're doing measurements online, the biolector is able to take a measurement and see if there is a difference potentially between your desired pH and then your actual pH. And if there's a difference there, the biolector can automatically respond to make sure that you always stay at your optimal pH. This then becomes really important, especially for Pichia, because at the lower pH ranges, we get more optimal results. So this was a really impactful example or experiment that we did with Pichia, where we're measuring the dissolved oxygen values of a particular, of the experiment, and at the time that carbon limitation happens, we can deliver a pulse of feed. So we call this the DO triggered fed batch example, where we're looking for the dissolved oxygen value to go low at a certain point. Generally, that's going to represent metabolism happening at that time. But then when dissolved oxygen value comes up again, that's generally when carbon has run out within your culture. So at that time, there's generally no more carbon to be used and metabolized. So because the biolector is taking measurements and can automatically use the microfluidic modules there, you can deliver a pulse of feed, in this case 3 microliters of glycerol, right at the time that the culture needs it, instead of manually doing a sample or manually doing an addition all at the same time. The biolector can then respond to its measured signals, which make a much more impactful example. So not only have we changed the polymer optode to be able to measure pH in a lower scale, we can then use the measured signals to, at a particular time, change the pH to really whatever we want, as long as it is within the range of that consumable. So in this case, we use about 5.5 to 8, but using the low pH plates, we're able to go much lower even than what's shown here. And I have an example of that, I think, next. This data really comes from, it's brand new data that we've just collected with the Biolector XT. It's within the poster hall right there if you really just want to see what the Biolector looks like and what the plates look like, and we can explain to you in much greater detail, I think, than what I can do here. But what we've done is taken a strain of Polymorpha, and at various pH ranges, this is a double-sided pH control using sodium hydroxide and hydrochloric acid as well. So we really get to see the effect that playing to the pH range of that strain and what the effect that really can be. So generally, our old pH optode, our old pH polymer, would have been much higher pH ranges. So in that case, about 6. But with our low pH polymer, we can now go to pH 4. And then we get to see the effect that difference in pH has on GFP production. So in this case, GFP will be produced after glucose has been depleted within the cells or within that broth. So we get to see the effect of different pHs on the growth. Now, I'm not sure if you guys can see the very slight color differences here, but there when we play to the lower pH range of the pH of 4, you then get a much quicker burst of GFP production than what you would have gotten with the pH of 6, which is what we previously were only possible to do. By making this change and going from kind of our old pH polymer to the new one, we have increased, in this example, we've increased the space-time yield of GFP production by almost double. So we basically end up, by playing to where the culture is at and what the culture really likes instead of just what we can provide, we really are able to make a more impactful experiment and get a quicker burst of GFP instead of waiting more hours basically for this burst to happen of what it would have happened otherwise. I really just think that, these are the new developments that we've had. Many people have heard of the biolector, but not sure that it would be applicable to Pichia strains because we previously couldn't play as low as we are now. But when we combine the fiber optics with the microfluidics and are able to, the fiber optic with the microfluidics and are able to use the low pH optode and our low pH plates, we can then create a more impactful experiment that plays much better with Pichia than we ever have before. And this is really only available in the biolector. You can see that in the poster hall. We have a kind of a shell if you just want to see what it looks like. We also have the plate itself. So if you'd like to see the optodes and kind of the microfluidic module, or the microfluidic plates, and just really how those play together, come talk to me after, after the talk is over. I think that is all. I just wanted to say, if you have any questions about, if you want to see any of these application notes that I've presented, it was a pretty quick talk, but if you want to see any of these application notes or hear more about the plates or the bioelector specifically, I'll be sitting at a table right over there.
Thank you. Thank you for the talk. Very interesting stuff. And I've been in high throughput for a long time, and that's great advances. My question is around Pichia with the extended fermentation times of 120, 144 hours. Is there any exhaustion of the chemicals in the optodes, or making them less responsive over time, or?
So 120 hours. I think we have data in our application notes that support up to 14 days.
Okay.
And we have customers that are using it for much longer. But if you want to test it out, you totally can.
Okay, thank you.
Hey, Shani, over here.
Oh, yes.
Thank you so much for a nice talk. Great to see that you guys can do the low pH now. That was a long time coming, I would say. But
Yeah.
I'm a great fan, so I will give you that up front from the bioelector itself. But how about methanol in your media? I don't think I saw the data, but any issues around the optodes there?
We do have a limit to the concentration of methanol, and actually if you come follow me after this, I'll show you the data sheet where it says what that limit is. I don't remember right off the top of my head, but some people have used methanol as kind of a manual addition. Pure methanol, as long as we'd have to be, what's the word? The plates are polystyrene, so you have to be compatible mostly with that. But if you wanted to do an addition up to a certain limit, we can accommodate. But come follow me for what that limit actually is.
Thank you.
Are there any other chemicals that can interfere with the functionality of the optodes and should be avoided?
In general, organic solvents just don't play well with, it's really polystyrene. I would love it if they, if we could, but the nature of the plate such that if it makes polystyrene cloudy, it will interfere with the measurements that you can take from the bottom half of the plate. So in general, organic solvents don't play too well, I'd say, with just the polystyrene. But if you want to test it out, we can send you a plate basically to test that out.
So this is a very neat gadget to optimize, to screen for good strains, correct?
Yeah, I'd say it's a strain screening tool.
So do you have any data on how frequent a false positive you would get or a false negative? In other words, have you taken some of these strains which performed differently and scaled them up and see whether the predictive fermentation characteristics of these strains scale up, and what is the predictive rate?
We have. It's not within this data here, or at least the presentation that I just presented, but we have data that supports 5, 10, 20 liters. Plus a lot of our customers are going up to pilot scale plant, levels. One of the problems that we have, and this is why we want partnerships, one of the problems that we have is that as soon as a company that would like to manufacture and sell a product, as soon as you use the bioelector and you get some really good data, then you don't publish it. So we can't really use that. But we do have data already that supports 5, 10, 20 liters, and then we have customers anecdotally that are using this as the upstream basically to going up to much larger pilot scale plant volumes. So we do have some data. I can show you some, and I might be able to link you basically with one of our customers that can act as a reference.